Hello, everyone. I'm Jordan Earls, the co-founder and lead developer of Quantum. And just in case you try and find me later, I woke up this morning with a fever, so I might be a little antisocial. But anyway, so GAF, just for those not aware, is basically a way of measuring how much computational resources a smart contract requires to execute. And so this basically prevents the common attack scenario of you make an infinite loop and suddenly you bring the blockchain to a halt. And so GAF basically mitigates that and makes people basically have to pay for whatever resources they use from the blockchain network. And so today I'm going to be talking about Ethereum and Quantum because they both share the same GAF model at the moment. Quantum is a tiny bit different, but not enough to matter. And so one of the biggest gas consumers of the Ethereum blockchain, as well as Quantum, is basically storage. So how do you store data on the blockchain? And so there's really 4 different ways of actually storing data. And so there's external code, which is basically where you create a contract, and instead of that contract containing EVM bytecode, it contains your data that you want to store. And then there's internal code, which is, of course, probably what everyone is familiar with when you just hard code something in the contract or pass it in through the constructor or whatever. It's constant code, can't be modified or anything like that. Then there's storage, which is basically the conventional storage that Ethereum uses. And that's like the general purpose, what most people use for their storage purpose or storage needs. And then there's transaction data. So in that, you basically, instead of actually storing data in the blockchain, you actually send it with each transaction. And then you store, like, say, a hash or something like that in the actual blockchain so that you can validate that they sent the correct data. And so just to give a quick overview of basically the cost of loading this data actually from the blockchain. So transaction is going to be the most expensive because you're sending it with every single transaction interaction with a smart contract that needs that data. You have to send that data along with it, and so it's very expensive. So it's more useful to actually exclude that green line that was transaction. And so this orange line here that goes up is storage. And so you can see it's actually cheaper to use storage for small amounts of data than the external code that is the blue line. And so under 128 bytes, it's cheaper to store it in regular storage, but for over 128 bytes, it's actually more efficient to use this weird create contract mechanism to store data as the actual contract bytecode. And then the cost to actually initially store that data, storage is actually the most expensive way, and it's the most commonly used. And then the blue line underneath that is the external code. So the external code is actually very cheap, or fairly cheap, to actually store data in, and like if you're never updating it. And then we have the internal code, which and then to actually update that storage, there's a variable cost as well. So the external storage, storing the data as the contract bytecode, is actually the most expensive to actually update that storage to like a new value or whatever. And that's because you basically have to redeploy the entire contract, because the Ethereum virtual machine does not provide a mechanism to actually update contract bytecode partially. You have to basically have the old contract self-destruct so that you get a little bit of a gas refund, and then you have to deploy an entirely new contract. And so the basic conclusions of this is basically that external code is the best for data that is seldom updated but commonly accessed, because it's extremely cheap to access. And then internal code, of course, is used for constant data that you know at deployment time. Of course, that's pretty obvious. You should always use internal code when you can. And then storage should be used for any data that's updated often, and also data that needs to be updated in a granular fashion, because storage you can, of course, update just one chunk of data, whereas with the external code method, you have to update the everything you store in it. And then transaction data is cheap for some use cases, but basically if you're using that smart contract more than once, then that cost very quickly escalates. And so if you have like maybe an escrow contract or something like that where you need to prove that the data is on, that the other person has the data, and you only need to send that data once, transaction data might actually be the most cheap way to do it. But if you need to call it 2, 3 times or more, then the costs quickly get very high. And so the rationale for expensive storage is a few different things. So the main reason I see is basically to make light wallet implementations of both Ethereum and Quantum faster to sync, easier to sync, and basically to allow for these lightweight nodes to download just a small amount of data rather than downloading a large amount. Also, storage is regarded as permanent. So there's kind of this, it's not really a misconception because it is permanent, but basically if you store the data in the blockchain, it's not actually like persistent on the blockchain itself, and I'll cover that in a second. And also, using more storage potentially slows down future accesses through the database, just because the database grows bigger and all of that. And so that rationale is really like quite wrong. So storage is actually free, like in a way. So if I deploy a 1 kilobyte smart contract that writes 1 megabyte of data, and then I go to sync the blockchain from a full node, I just download that 1 kilobyte smart contract and then execute it. The storage is never actually stored on the blockchain. It's tracked using a state root hash, basically like a Merkle tree and a hash tree, so that it can be validated quickly. But the storage itself does not have like a fundamental cost to actually like using the blockchain. And and one of the alternatives to storage is the external contract code method that I discussed earlier, where you store the data as bytecode in a contract. And so this method is cheaper in some cases, but it's actually very bad for SPV wallets and light wallets that only sync the state, don't sync the entire blockchain. And that's because basically you download the contract bytecode, you download the data and everything, and then you start executing it, and then it calls out to another contract and needs to download data from that. So then your phone or whatever has to open back up the network connection, download that data, and then continue execution, and then it might need another contract as well. And so it adds a very real layer of latency and lag over that experience. And also, external code is actually loaded completely in both Ethereum and Quantum implementations. And so what that means is there's no way to really like just say, okay, I want bytes 200 to 300 of this contract bytecode. You have to load the entire contract, execute it, and then the contract code itself, or no, you don't have to execute it, but you have to basically load the entire thing into memory and then use like an external copy command or whatever it is to actually copy that, just a chunk of that data. And also, storage is relatively cheap, but on IoT devices, things with very limited processing power, it's many times more useful to actually cache computationally intense data to the blockchain. And basically the way that this gas model is designed is that this is very expensive to cache, so you prefer to instead execute it. And so I'm going to talk on another topic, which is kind of a favorite of mine, and that's comparing just if two strings are equal. So foobar equals foobar, is it true? And so I use 4 different implementations with a varying amount of data and everything, and only like complete like equal strings. And so string utils is one used by a lot of smart contracts out there. It's a very commonly used library. And then string slice is a little bit more powerful of a library, more efficient, and provides a little bit more functionality, but also it's a little bit thicker to deploy. And then there's a naive loop implementation, which is basically where I just wrote a for loop, compare each character, and if all true, then return true or whatever. And then using SHA-3 comparison. So basically, is the hash of this string equal to the hash of this string. And so the actual cost of this ends up being string utils is the most expensive. That's the blue line. And then slice is actually the green. It's the green line, but you can't really see it. And then naive is the second line. And this is, of course, with gas cost and everything. And then the SHA-3 is actually the cheapest method of doing this. Slice is slightly more expensive, but the resolution is so small that you can't tell. But if you look at the numbers, it actually is. And so what's the takeaway from this is basically SHA-3 is the cheapest for some reason. And SHA-3 actually takes about 28 milliseconds to hash 100 bytes of data. And a native string equality, like on a regular processor, takes less than a millisecond. So why exactly is SHA-3 actually cheaper? And it's not just because Ethereum is badly designed or anything like that. It's that gas models in general are absolutely terrible. They're at best an approximation and amortization of the cost of the resources of the blockchain. And it runs on multiple processors. It runs on ARM, x86, probably other IoT devices. And so because of this kind of separation between this, it doesn't include the nuanced optimizations and caching. So modern processors have pipelines, caching, a lot of different optimizations that are extremely complicated. And so basically, it ends up being like kind of a worst case scenario of trying to have the most expensive, like the most fair gas cost. And so there are some ideas that me and our team at Quantum basically have for improving this. And one of the big ones is basically providing a rich and predictable standard library with specialized gas costs. So you might have like a string compare library or string compare function that's already in the blockchain, kind of like a precompiled contract or something like that. And its gas cost is fixed. It has a set rate fee or whatever. And that is all analyzed by a human. And the problem with that is, what if you set it too low? What if you set it too high and it becomes unusable? So Quantum's decentralized governance protocol mechanism actually mitigates some of this because it basically allows for parameters like these to be adjusted on the blockchain without any kind of fork, no disruption, anything. It's basically just the governance parties come together, they vote on a proposal to reduce the cost of the string compare function by 10 gas or whatever, and then everyone votes on it, and if it gets all the votes, then it passes. The blockchain automatically forks. It automatically basically begins working with this new parameter, and smart contracts can take advantage of it instantly without having to download a new wallet or anything like that. And another idea is basically having a cost for branches and memory, not for actual computation operations. So computation is relatively cheap, usually on the order of nanoseconds. But whenever you branch and the processor mispredicts that branch, or it has to flush a pipeline, or you access some memory and it's not in cache, that takes that nanosecond operation into the order of milliseconds. And it was basically the actual most expensive operation, even though if it's predicted correctly, then it's one of the cheapest operations. And another idea is basically to measure macro operations. So you would have like a template or whatever of basically these operations that are more than just one opcode. It's like a series of opcodes with a branch or whatever, and based on if it's predictable and everything and been human analyzed, then this basically can be made cheaper or more expensive even. And then the great problem with making a comprehensive gas model that is efficient and good, basically, and usable, is that at some point it becomes more expensive to actually measure the gas cost than it does to execute the actual code. And so that is probably one of the greatest problems in this entire space of making this game theory and everything, that basically encourages good blockchain citizens because it's the cheapest way to do it. And so we will always be a fundamental problem with this. And so I actually wrote a blog post to accompany the speech, and So it has like the data, the graph, the formulas I used, and some of the example code. And that is at earls.net, EARLZ.net. And you can also read some other stuff about quantum there and everything. Yeah. Thank you.
Thank you very much.